Welcome to our practice exam final video. We are first starting here looking at a stem and leaf plot for data. These are numbers of meters walked during physical therapy by patients with peripheral artery disease, and they want us to interpret the results. So for us, remember, that means center, outliers, spread, and symmetry. So stem and leaf plot, remember what you want to do is put for this data, we've got tens digit and ones digit. So you're going to put your tens digit as the stem and your ones digit as the leaf. Looks like our high here is 131 and our low is 58. So we're going to go from 13 tens down to 5. Our vertical bar here, and then the 131 will have a 1 here, 90, 109, 58, and so on. So 96 and 85, 113, 124. Oh, I forgot my 10s there, or my 11s. Uh, 117, 102, 92, 105, and then a 108. And then remember, we want to reorder this data so that we're increasing. So here we want to go 2, 5, 8, 9. And you want to try and line the numbers up. So we got all the first numbers in the list, second, third, etc. So this one we want to go 0 to 6. Switch the 6 and the 2. So there's our stem and leaf plot. So for the center of the data here, looks like the center of these is somewhere in the middle of the 110s, or I'm sorry, the 100s. So for your center, the middle of the hundreds would be 105. So we could say approximately 105, somewhere in the hundreds. And then outliers, there's a gap in the data. Remember to show the gaps in the data because that shows how things are distributed. So there's a gap in the data, and here's this 58 all down there by himself. So he's an outlier, probable outlier anyways. Spread of the data, this data is pretty concentrated here. I mean, you've got that one outlier, but so it's spread from the 90s to the 110s. So we could say concentrated. Uh, 90s to the 110s. And then the symmetry. So if we draw our curve along the top of the data, we see that's fairly symmetric, but there's a slight skew. If we drop out that outlier, then it's still a slight skew, but this is fairly symmetric data. So there's some leeway here. You could say that there's a slight skew. You don't have to say which way. But it is fairly symmetric. It's just very slight skew. Mean, median, and mode of the data, 10, 50, 20, 50, 40, 10. So remember, all of these are measures of central tendency or the middle of the data. So first the mean, and this is sample data. We'll use X bar for the mean. Remember, what you want to do is just sum the numbers, divide by the number of numbers. So 10 plus 50 plus 20 plus 50 plus 40 plus 10. And there are 6 numbers in this list, so we are dividing by 6. So if you enter this into the calculator, you will get a total of 180. Divide by 6 gives you a mean of 30. So for the median, remember that you need to reorder the data. Don't forget to reorder. So from smallest to largest. So we had 2 10s were our smallest values. And then we've got a 20, and then a 40 and 2 50s. So we can see here that we've got 2 middles because there's an even number of numbers. The 3rd and the 4th are our middles. And remember that your median, we use x tilde for median, is the average of 2 middles if you have 2 middles. So it's either the middle value or the average of the 2 middles. So 20 plus 40 divided by 2 again gives us 30. Notice that mean and median are the same, which means that this data is pretty symmetric. It's not a skewed distribution. And then the mode is actually the most frequent value. And what we see here is that we've got 2 10s and we've got 2 50s, so we've got 2 modes. So 10 and 50 are our modes. Range and standard deviation of the data. So these are measures of spread or variation in the data. So remember that the range is the high minus low. And so our highest value is 10, our lowest is 1. So 10 minus 1 is 9. So there's our range. That's the easy one. And then for our standard deviation, I am going to use the shortcut formula here. So I'm going to make a table of x and x squared. And remember what our shortcut formula is. So here's our exam 1 formula sheet, and we're doing sample variance, which is this formula here. So let me grab that and bring it back over. That's the shortcut formula. So in order to do that, we need the sum of the x's and the sum of the x squares. Now you can do this in your calculator using stat and one variable stats, and that's fine. So we've got our values here of 1, 4. Let me go ahead and put these in increasing order here. So we had 1, 3, 4, 5, 7, 10. So squares here then are 1, 3 squared is 9, 4 squared is 16, 5 squared 25, 7 squared 49, and 10 squared 100. Put our totals down here on the bottom. So if we sum up all of these x values here, we will get a total of 30. If we sum up the squares, we will get a total of 200. So then, our sample variance here, we do the sum of the squares, that's the 200, and then minus the sum of the x's, that's the 30, that gets squared on top, and then divide by n. N is 6, there are 6 numbers, and then divide the whole thing by n minus 1, 5. So if you enter this into the calculator, this 30 squared is 900 divided by 6 is 150. So this is 200 minus 150. Divide by 5, that's 50 divided by 5, which is 10. And then to get the sample standard deviation, you take a square root. Take a square root of s squared. And that square root is approximately 3.16. So remember, standard deviation is a better measure of variation than range because it uses all of the data values. The range is just a rough estimate. Next up, we're given some data, some x and y values here. 1357, 2547. Draw a scatter plot of the data. So that's just x versus y. So here, let's see, x is 1 when y is 2. So that would be 1 to the right and 2 up right here. When x is 3, y is 5. So 1, 2, 3 to the right, 1, 2, 3, 4, 5 up right there. When x is 5, y is 4. 2, 4, 5, 1, 2, 3, 4 right there. And then when x is 8, y is 7. 6, 8, 2, 4, 6, 7 right there. So there's our data. We can see that a line of best fit should go down through the center here. It probably should go almost through these 2 points here, and then have each of these one on each side. So part B, we want to find that equation of the regression line, the best fit line. So let's go back to our formula sheets. I want to have all of these for the exam. So this is exam 2 formulas. So coefficient of correlation, least squares of regression line. There we go. So we need that sum of squares of x and sum of squares of xy, which is these guys here. So let's take those and bring them over. And actually, let's see what else we're up for here. Graph the regression line. What does the R value? We will need a coefficient of correlation. So let's go ahead and bring our slope formulas over. So we've got slope and y-intercept there. Actually, let's do this. Our sum of squares of y here, sum of squares of xy there. And let's go ahead and do our slope here. And y-intercept there. So we don't need a table of values here. You can just do from 2 variable stats. So 2 variable stats. So let me remind you how to do that. So here's our TI-84. Remember, we want to go to stat and edit. If you've got numbers in your list, go ahead and do clear enter and clear them out. And then we just want to type our data in there, pressing enter as we go. So we had 1, 3, 5, and 8 for our x's. 1, enter, 3, enter, 5, enter, 8, enter. Arrow over to our y's. We had 2, enter, 5, enter, 4, enter, 7, enter. Okay, so there's our data. We're going to go to stat again, over to calc, and then we want 2 variable stats, which is option 2. Our lists are the way that we have them. List 1 and list 2 are x and y, and we enter. So we've got our sum of x's is 17, and our sum of x squared is 99. And then going back here, arrow down. Sum of y's is 18. Sum of y squared is 94. And then sum of xy is 93. Alright, so sum of squares of x, the variation in the x values, sum of x squared, which is our 99, minus the sum of x's, quantity squared over n. Remember, n is 4, there are 4 data points. Sum of the x's is 17, so we get a 17 squared divided by 4. And if you enter that into the calculator, you will get 26.75. Sum of squares of y, so we got the sum of the y squared values, that's 94. Minus the sum of the y squared over n, that's 18. So 18 squared over 4. We enter this in, and we will get 13. And then the sum of the xy's, that's the 93 right here, minus sum of x, sum of y over n. So the sum of the x's is the 17, the sum of the y's is 18, and we're divided by 4. And if we enter that into the calculator, we get 16.5. So then our slope is the sum of squares of xy, which is the 16.5, divided by the sum of the squares of the x, which is the 26.75. And if you enter that into the calculator, you will get approximately 0.616822. Remember, don't round off until the very end because we need that to calculate our y-intercept b. So this is the sum of the y's, which is the 18, minus our slope from up above, 0.616822, times the sum of the x's, that's 17, and then divide that whole thing by 4. Now this one we can go ahead and round. So here I get approximately 1.88. And so this one we can round off to 0.62. So then our estimating line, y hat, is equal to mx plus b. And our slope is 0.62 times x plus our b is 1.88. Draw the graph of the regression line on the scatter plot. So our y-intercept is 1.88, so a little less than 2. Let me do my dot in a different color here. So 1.88, about right there. And then we need one more point. Well, it's a little hard to, rise 0.62 units and run 1 unit, because remember this is 0.62 over 1 as our slope. So what we could do is we can do a little table of x and y values. We've already got one value. When x is 0, y is 1.88. That's the y-intercept here. And then why don't we do, say, x equals 10, and go ahead and plug that in. So 0.62 times 10 plus 1.88. So 0.62 times 10 plus 1.88. So 8.08. So go 10 to the right and 8 up. So 2, 4, 6, 8, 10, 2, 4, 6, 8, about right there. And then we can sketch our line through the 2 black points. And there we are seeing our regression line almost go through those two ending blue points, and then these have got one on each side, just like we thought it should. And then next up, we are asking, what does the value of R, remember the coefficient of correlation, tell us about our relationship between X and Y? So in other words, interpret R. So we first have to find R. So remember that our R value, let's go back and grab our formula here. So R value right there. So this is going to be the sum of the squares of the xy up on top, that's the 16.5. And divide by square root of sum of the squares of x down on the bottom, that's our 26.75. Times the sum of squares of y, which is the 13. And if you plug this into the calculator, you will get approximately 0.88. So this is a positive coefficient, which means that it's a positive relationship. It's pretty close to 1, so this is going to be a strong positive linear relationship. So remember that the coefficient of correlation, R, only tells the strength of linear relationships. So if there's some other type of relationship that's not linear, it doesn't tell us anything about that. So that is chapter 2. It's your representative question from chapter 2. That was probably one of the most important ideas on that test. Next up, we've got a review of probability here. So table here shows the number of people that have a certain disease state given their smoking status. So we've got smoker and non-smoker. Those events are represented by S and NS. And then we got victims of stroke, ST, lung cancer, C, and emphysema, E. Got totals on the rows here, total on the column on the bottom. So person selected at random, find the following probabilities. So the person has lung cancer. So there's no given probability here, so it's desired out of total. The total is 95. The number to have lung cancer are 23. So 23 that have lung cancer out of 95 total. Don't need to change it to a decimal, don't need to reduce. Person is a smoker and has emphysema. So smokers are in this row, emphysema in this column. That 21 is both in the smoker row and the emphysema column. So that's our desired outcomes, 21. And then the total outcomes is 95. A person is a non-smoker or has had a stroke. So remember, or means that you're going to add the probabilities together, but you have to subtract out the overlap. So remember the symbols for this are, you do NS as your non-smoker, or stroke is ST. So remember what you do is you take the probability they're a non-smoker and you add the probability that they had a stroke, and then you subtract out the overlap, probability of non-smoker and stroke. So non-smokers, those are 40 here in that non-smoker row, so 40 out of 95. Plus the people that had a stroke, there were 43 out of 95. But remember, we've done some double counting here. This 28 right here, that's in the non-smoker row. Okay, it's in that row, but it's also in the stroke column here. It's in the row and the column. So that got counted once in the 43 and once in the 40. So we need to take that out, subtract that 28 out. So we're going to subtract out 28 out of 95. And if we do the calculator work there, we will get 55 out of 95. Person has had emphysema if we know that they're a smoker. So now we have a given condition. It's given here that they're a smoker. So that means that they're in this first row. So that restricts our total outcomes of 95 down to 55. So this is, again, probability that they have emphysema given that they are a smoker. So this given condition restricts the total outcomes down to 55 because we're just in the first row. And then out of that 55, how many had emphysema? 21. So 21 out of 55. Person does not have lung cancer given that they're a non-smoker. Okay, so this one we've got a not in there. That's a complement. So we're asking probability that they are not a smoker, and so let's see here. I'm sorry, probability that they do not have lung cancer. So this is not C, and it's given that they're a non-smoker. So given NS. So they're given that they're non-smokers. So non-smokers were the second row, which is a total of 40. And out of those 40, how many did not have cancer? So out of these 40, 8 had emphysema and 28 had stroke. Only 4 had lung cancer. So this is going to be the 28 plus 8. So that's 36 out of 40. And then lastly, are the events S and E independent? So smokers and emphysema. So remember, mutually exclusive means overlap. So if I was asking mutually exclusive, they're not mutually exclusive because they have overlap. But independent is asking, well, if you look at the probability a person's a smoker and then compare that to the probability that they're a smoker given that they've got emphysema, if those two are the same, then the events are independent. If they differ, then they're dependent. So smokers, let's see, smokers, we've got 55 out of 95. And then smoker given emphysema. So it's given that they have emphysema, so we are restricting to 29. And then out of those, how many are smokers? So we had 21 out of 29. And if you want to convert these to decimals, you can double check. These guys are not equal. So are they independent? No, they are dependent. The probability of one outcome depends on the other. Because, see, it changed given that they had emphysema. So these probabilities do, or events do affect each other. And then lastly here are the events S and E mutually exclusive. So smokers we've got right here, and then emphysema is right here. And they're asking, are those events separate? No, there's 21 in the overlap. So no again, there is overlap. And problem number 5, now we're looking at a probability distribution. So remember, this is all the outcomes of an experiment and the probability of their outcomes. The random variable here is the number of patient inquiries in a 15-minute period. So X is the number of inquiries, and then P of X is the probability that that many inquiries would occur. What is the average or the expected number of inquiries? So in other words, that's the mean of the distribution. So if we go back to probability distributions in our formula sheet here, so let's see, that is exam 3 now. So we've got mean here of a probability distribution is the sum of x times p of x. So we have to do an x p of x table to find that mean. So we are going to list the x values and then the probability of x, and then we're going to multiply those, x times probability of x. That's going to give our mean after we sum them up. So our x values are 0 through 7. And then those probabilities are 38%, 25%, 18%, 7%, 5%, 4%, 2%, and 1%. So we're going to multiply straight across. 0 times anything is 0. 1 times 0.25 is 0.25. 2 times 0.18 is 0.36. 3 times 0.07, 0.21. 4 times 0.05, 0.20. 5 times 0.04, 0.20. 6 times 0.02, 0.12. And 7 times 0.01, 0.07. Now when you sum up the probability column, that should sum up to 1.00. We sum up the x times probability of x column, we get 1.41. Okay, that's our mean. So our mean here is the sum of the x times probability of x formula, which is 1.41. Part B, what is the standard deviation of the distribution? So this is a discrete distribution. So our standard deviation, well, here's our variance. And then standard deviation, you take the square root of that. So let's grab that variance formula and bring that over. So we need the sum of x squared p of x. So we want to add one more column here on our table. This is going to be x squared times the probability of x. So we got 0 squared times 0.38, that's a 0. 1 squared times 0.25, still 0.25. 2 squared is 4 times 0.18 will give us 0.72. 3 squared is 9 times 7, 0.63. 4 squared is 16 times 5 is 0.80. And 5 squared is 25 times 4 is 1.00. 6 squared is 36 times 2 is 0.72. 7 squared is 49 times 0.01, 0.49. Sum up all those and we get 4.61. So let you check the calculator work there. And now we are ready to find our variance here. So that's the sum of the x squared p of x column. That's the 4.61. And we're subtracting our mean squared. So that's our 1.41 squared. And if we do the calculator work here, we get 2.6219 to 4 decimal places. And then our standard deviation is going to be the square root of that, 2.6219. So if we take that to a couple decimal places, we get 1.62. Part C asks, what's the probability of at least 4 inquiries? So this is asking for the probability that x is greater than or equal to 4. So greater than or equal to 4 means that our random variable x is either 4, 5, 6, or 7. It's actually 4 or 5 or 6 or 7. So or means that you add the probabilities. So we're going to do 0.05, 04, 02, and 01. So let's see, what is that? 910.12. So 12% chance that we'd have at least 4 inquiries inside that 15-minute time period. Next up, we are dealing with a binomial random variable. So remember, this is where you have only 2 outcomes, success and failure. Our sample size or number of trials is 11, so that's your n. So n is equal to 11. P is 0.6, that's your probability of success. And we are going to use the calculator to compute the following. So remember here, for binomial probabilities, you can only have whole number values. So the probability that x is strictly less than 4, well, x can only be 0, 1, 2, 3, 4, up to 11. It can't be any numbers in between. So if you're strictly less than 4, that means that your probability is less than or equal to 3. So it's probability x less than equal 3. And less than equal probabilities, that's what Binomial PDF gives for us. So we want to do Binomial PDF here. CDF, because we are summing from 0 up to 3. So this would be BinomialCDF. And then we want to put the 11 in there, which is our total number of trials, the 0.6, the probability of success, and then we are going up to 3. And let's go ahead and enter that in the calculator. So let's see here. We want to go to second variables, and then binomial PDF. Head on down here. CDF, excuse me. Enter. Trials were 11. P is 0.6. And we want less than equal 3. So 0.029 to 3 decimal places. So 0.029. Probability that x is greater than equal to strictly less than 6. So this is saying that so the x values that are covered in here are going to be 2, 3, 4, or 5. 6 is not covered because strictly less than 6 means you're 5. So we're going to do, remember, our binomial CDF gives less than equal probabilities. So we want to do less than equal 5 and then subtract off 0 and 1. So 0 to 5 minus 0 to 1. So this will be a binomial CDF, excuse me. Binomial CDF. And we've got 11 trials, 0.6 probability. We're going to go from 0 up to 5 first, and then subtract off binomial CDF, and this will be 11 trials, 0.6 success, and we're subtracting off 0 and 1, so up to 1. So let's go ahead and enter that in. So let's clear this out. We're going to go to second variables, go down to binomial CDF again, which is B. And trials 11, 6, we're going up to 5. And then minus, we're going to do the same thing again, second variables, go down to B. And then we're going to put in x equals 1. So now we've got a difference of 2 of the binomial CDFs. So 0.2457, so 246. So 0.246 to 3 decimal places. And then lastly, in this problem, they want mean and standard deviation. So let's go back to our formulas. So for binomial probabilities here, two outcomes, repeated trials. We won't be using binomial probability function, but we do want our mean here, n times p, and our standard deviation of np 1 minus p square root. So let's grab those guys, bring them over. So there are 11 trials times 0.6 is our success, and that gives us 0.66. And then this will be the square root of 11 times 0.6 times 1 minus 0.6. And if you enter this one into the calculator, you will get about 1.62. Let's double check that real quick. So let's see, clear out. So we want a second square root, 11 times 0.6, and then parentheses 1 minus 0.6, close up our parentheses, enter. Yep, 1.6248. So that's binomial probability. Now, if I state this problem as a word problem, you remember in here binomial means two outcomes. So anything where you've got two outcomes, success and failure, and your random variable can't take on anything in between, you're going to use binomial. Now, on the other hand, if your data is continuous, it takes on every value in a range. I should actually tell you that things are normally distributed. So if you've got a normally distributed random variable, now you're going to use normal CDF and inverse norm. So we're given a normally distributed random variable, got a mean of 10.5 and a standard deviation 2.1. We're first finding probability that x is less than 9.9. So let's sketch our bell-shaped curve here. So we've got our mean is 10.5, which is in the middle. And then we want to know what's the probability that a random value is less than 9.9. So 9.9 would be down here someplace. We want this left area. So this is going to be normal CDF. And then remember what you do your lower bound here, which is like negative 1,000, and then our upper cutoff 9.9, and then we do our mean, which is 10.5, and our standard deviation, which is 2.1. So let's go to the calculator and do that real quick. So we're clearing out here, second variables. Normal CDF is option 2. So our lower bound 1,000, our upper 9.9, enter, mean 10.5, standard deviation 2.1. And we get 0.3875. So that is that area right there. Remember, you should never get anything less than 0 or greater than 1. Otherwise, you did something wrong. You should check your work. Probability that x is between 11 and 12.5. So that's our lower bound or upper bound. So this will be another normal CDF. And we've got that same bell-shaped curve here, with 10.5 in the middle, and 11 is a little bigger than 10.5 up here, 12.5 even farther out, and we want the area that's between those. And remember, it doesn't matter whether these are less than or less than equal, you do the same thing. So normal CDF, our left cutoff is 11, our right cutoff is the 12.5, our mean is 10.5, and standard deviation 2.1. So if we enter those in real quick, So I'm going to go to second variables, normal CDF. Let's see, my lower is 11, upper 12.5, mean standard deviation are the same. So 0.2355 if we round up here. And again, that represents not only probability, but also represents that area. So probabilities are areas under the normal curve. So again, if I give this as a word problem, you want to look for these words here, normally distributed. I have a normally distributed random variable. So I could say, for example, I have birth weights that are normally distributed. The mean birth weight is 10.5. The standard deviation is 2.1. What is the probability that a birth weight's less than 9.9 pounds? Or what is the probability that a birth weight is between 11 pounds and 12.5 pounds? So that's how that would be asked in the context of application. And then number 8. So I've got a random sample of 45 newborns. This yields a mean birth weight of 8.3 pounds. The population standard deviation is 2.7. Construct a 99% confidence interval. So this is from exam 4. Our random sample of 45 newborns, so we know n is equal to 45. The mean birth weight is 8.3 pounds. That's our sample birth weight, so that's x bar. And then they give us population standard deviation is 2.7, so that's sigma. So we know sigma, so we're going to be using z-values. So sigma is 2.7. We want a 99% confidence. 99% confidence means alpha is 0.01. And remember that, let's go to our formula sheet here. Our confidence interval looks like this. So it's x bar plus or minus z alpha over 2 divided by root n. So let's grab that formula and bring him over. And then remember that we've got that table of common values here. We want 99% confidence here, so our z-value is 2.575. That's our z alpha over 2. So, so this implies then that our z alpha over 2 is 2.575. So our x bar, that's our 8.3. And we are going to add and subtract here the z-value, 2.575, times sigma, which is the 2.7, divided by root of the sample size, square root of the sample size. Remember, that's the standard deviation of the sampling distribution. So your margin of error is this quantity out here. Let's figure that one on the calculator real quick. Let's see, clear u out of there. So we've got 2.575 and times 2.7 divided by square root 45. So 1.036. So 1.04 to 2 decimal places. So this is 8.3 pounds plus or minus 1.04. So 8 minus 1.04 will give you 7.26. And then 8 plus 1.04 will give you 9.36. So that's our lower confidence limit, upper confidence limit. Now if I ask you to interpret what that means, so we're 99% confident that the true population mean, so that mu, population mean birth weight, is in the interval 7.26 to, oh, I'm sorry, that's, yeah, that's right, 9.36. 9.36. And then remember the 99% confident. If I ask you to interpret what the 99% confident, what that means, remember that 99% confident here, what that means that is that 99% of repeated samples will give confidence intervals that contain the population mean. Mu. So it's a statement about the proportion of repeated samples, repeated confidence intervals that are going to contain that true population mean. So now if I gave you sample standard deviation, so if I give you S, then that implies is that you need to use t-values. Okay, so if you have sample standard deviation, you're using t-values. So remember what those formulas are. Come down here. So this is sigma is not known, so you have sample standard deviation instead of population standard deviation. So that means that you're going to use t-values here. So not t-table, but you're going to use t or inverse t. So you've got your t alpha over 2 is your multiplier, and then you're using S instead of sigma. So that's the difference there. And remember, the difference with hypothesis testing, you're using t-values, t-test. So you're going to you're going to have inverse t for your cutoff, and then your test statistic is actually a t-value instead of a z-value. And remember, with population proportions there, whether you're doing a confidence interval or a hypothesis test, you're always using z-values here. So let's go back. We got one more question here. So that was a confidence interval, and now you've got an example of a hypothesis test. So current studies show that STD rates in teens are alarmingly high. Out of 300 that were randomly selected school students in Illinois, 81 are found to have sexually transmitted diseases. CDC estimates the national infection rate is actually 24% among high school students. I don't remember if I looked this up and quoted a number that was pretty close to real statistics. I would not be surprised. We want to use a hypothesis test. Okay, so we're doing a hypothesis test with alpha equals 0.05 to determine if the infection rate. A rate is a ratio or a proportion. So a rate is equal to a proportion. So we're doing a hypothesis test of proportion. To determine is Illinois higher than the national average? Higher. So we're testing higher than the 24% national average. So out of 300 randomly selected, that 300, that is our n. So n is equal to 300. And 81 were found to have sexually transmitted disease. That's our value x, which is number of successes. So quote unquote success. I don't know if I would be feeling like I had a success if I had a sexually transmitted disease. National infection rate is 0.24, is 24%, which is 0.24. So that is our P0. That's our hypothesized proportion, 0.24. And alpha is 0.05. And then we're testing, is the the rate, the proportion higher in Illinois. So this is step 1. Remember what our steps are here again. Go back to formula sheet here. So we've got hypothesis test for proportion. Okay, these are our steps. Why don't we go ahead and bring those over. So we're dealing with proportion. So we've got our givens. Want to write our null and alternative hypothesis. So H0 and HA. So remember, the alternative is what you're trying to show. We're trying to show that Illinois is higher. So that would be that the proportion in Illinois is greater than 0.24. If that is not the case, then we'll say that P equals 0.24. There's no change. Step 2, we are going to draw our distribution curve and then mark the rejection regions. So this is an upper tail test. So we're going to draw that distribution curve. Our rejection is on the right-hand side. So reject H0 up here. And then the cutoff for that rejection region, so alpha is 0.05. We can get this from the test of common values here. So go back to our formula sheet. Remember, we use z values with proportions. So we can go back to our list of common rejection regions, cutoff for rejection regions. So here's rejection regions for common alphas. This is an upper tail test, 0.05. So 1.645 there. So this cutoff is 1.645. And then we, step 3, compute our test statistic. So then that, again, is P prime minus P0. You know what? Let's go ahead and compute our P prime here. That's the sample proportion. That is X divided by N. That's also on the formula sheet. So that's going to be the 81 divided by 300. And 81 divided by 300 is 0.27. So that's higher than the 0.24, but is it just due to chance or is it significant? So step 3, we're going to calculate our test statistics, z-test. So we are going to do the sample proportion minus the hypothesized value. So that's 0.27 minus 0.24. We're going to divide by the standard deviation of the sampling distribution. So that's P01 minus P0 over N. P0 is the 0.24. Remember, you assume 0.24 unless proven otherwise. Innocent until proven guilty. So 0.241 minus 0.24 divide by our N there is 300. And you probably want to use horizontal fraction bar when you enter that in the calculator. So I did that and I got 1.22. And so that 1.22 is less than 1.645. So right here is our z-test. It is not in the rejection region. So step 4. We reject if z-test is in the rejection region. Our z-test, which is 1.22, is less than the 1.645. It's not more extreme, so we do not reject. H0. So in formal language, we would say that there is not sufficient evidence to reject the null hypothesis. And then we finally state our conclusion. So we're going to conclude that the STD rate in Illinois is not any higher. So we conclude that P is still equal to 0.24. So the STD rate for Illinois is not higher than the national average. At least not from this sample information. It is not extreme enough. All right, so that wraps up our practice exam. So these topics are representative of some of the most important topics from each chapter. So generally the final exam should be pretty close to what we've done here. Although, especially here, proportion, I'll do one problem with proportion, and then remember I said I was going to do one problem with the t distribution. So if I did here a confidence interval or a hypothesis test with the t distribution, so remember that's when you're given S. If you're given S, you have to use t values. So those will be our two problems there at the end. So it should be about the same length as the practice final exam also. I'm trying to be selective here and not go overkill with number of problems. So you'll also want to look over your old hour exams. If you understand the problems on the practice exam and the problems on your hour test, you should be in good shape.